Hey there, and welcome to today's Explainer. If you're the kind of person who just loves to strip away all the noise and get right down to how the physical world actually works, well, you are in the perfect place. Today, we're going to demystify the physics of straight-line motion, which scientists call kinematics. And to do this, we are absolutely not going to use abstract, confusing textbook examples. Instead, we're going to use a real-world analogy that we can all intuitively understand, a simple car trip.
Picture this. You're driving down a perfectly straight road, enjoying the drive, and suddenly, you spot a hazard ahead. You slam on the brakes, and the car eventually screeches to a halt. But what physically and mathematically is actually happening during that specific window of time? By unpacking that exact high-stakes scenario, we're going to master the fundamental rules of motion.
All right, so here's our roadmap for today. First, defining the straight line. Second, average versus instantaneous velocity. Third, the rules of acceleration. Fourth, visualizing the math. And fifth, we'll wrap up with some real-world driving math. Let's dive in.
Okay, starting right off with Section 1, defining the straight line. So, a car is a really complex machine, right? Spinning wheels, moving pistons, a whole bunch of moving parts. But in physics, to understand basic movement, we use something called the point-object approximation. We basically simplify that entire complex car into a single mathematical dot. Imagine a diagram showing a perfectly straight horizontal path, our x-axis, with a starting point marked as 0. This represents rectilinear motion, which just means movement confined to one single straight line. And this is actually the perfect moment to clearly define distance versus displacement. Distance is just the total ground covered. Think of your car's odometer. It just keeps ticking up no matter which way you drive. But displacement, which is what we really care about here, is simply the straight line difference from your starting point to your final position on this axis. It's the net change.
Moving right along to Section 2, average versus instantaneous velocity.
You know, there's a huge difference between these two concepts. Average velocity happens over a measurable time span. So if you say, I averaged 50 kilometers per hour over my 2-hour road trip, that's your average. It's just your total displacement divided by your total time. But what if a police officer with a radar gun clocks your speed at exactly 4 seconds into your trip? That is instantaneous velocity. It happens in an infinitesimally small instant. It's the exact physical reality of looking down at your speedometer for one specific fraction of a second.
Now this is where things get really cool, because this idea visually connects basic algebra straight to calculus. Average velocity is just the slope of a line connecting two distinct points on a position time graph, say where you were at 1 second and where you were at 3 seconds. But as we shrink that time interval down closer and closer to 0, those 2 points practically merge. That connecting line morphs into a tangent line that just barely grazes the curve of the graph. The slope of that specific grazing line, that is your exact instantaneous velocity.
All right, up next is Section 3, the rules of acceleration. Hundreds of years ago, Galileo realized something mind-blowing while studying falling objects. He figured out that gravity didn't change an object's velocity based on distance, but rather it changed velocity uniformly with time. Mathematically speaking, just like velocity is the slope of your position curve, acceleration is simply the slope of your velocity curve. It's the differential coefficient of velocity with respect to time. It describes exactly how fast our car is speeding up, slowing down, or changing direction.
Now here is a massive misconception. A negative acceleration does not automatically mean you are slowing down. Seriously. If your car is moving in reverse, so in the negative direction, and your acceleration is also negative, you are actually speeding up in reverse. The ultimate rule of thumb is just this. If your velocity and your acceleration are acting in the exact same direction, you speed up. If they are acting in opposite directions, fighting each other, your car is slowing down.
Which brings us to Section 4, visualizing the math. Let's see how all of this builds together.
Think of all these concepts mapping out perfectly onto a ladder of kinematics. Position is at the very top, velocity is right there in the middle, and acceleration is on the bottom rung. If you want to move down the ladder, you differentiate, meaning you find the geometric slope of the curve. But if you want to climb back up the ladder, like say you know your velocity and you need to find your total position change, you integrate. You find the accumulated area under the curve.
To really see this in action, imagine you're traveling at a constant velocity. On a graph, that's just a flat horizontal line. To find the area underneath this line, you just multiply the height by the width. The height is your velocity in meters per second. The width is your time in seconds. When you multiply them, the seconds literally cancel each other out, leaving you with just meters. The geometric area of that rectangle is literally the physical displacement of your car.
But what if you are stepping on the gas, accelerating, and creating a sloped velocity line? Well, you don't need to blindly memorize a bunch of terrifying textbook equations. The total area under that sloped line breaks down beautifully into just a basic rectangle plus a triangle. The area of the bottom rectangle is your initial velocity times time. The area of the top triangle is 1/2 the base times the height, which gives us 1/2 acceleration times squared. Just add those two simple geometric areas together, and boom, you have just built the fundamental kinematic equation for total displacement from scratch.
Finally, let's bring it all home with Section 5, Real-World Driving Math. Let's look at the timeline of a driver spotting a hazard and trying to stop. It is really broken into two distinct phases. First, you have the human gap. This is your cognitive reaction time. It literally takes about 0.2 seconds for your brain to observe the hazard and physically tell your foot to hit the pedal. During that tiny window, your acceleration is 0. You are still coasting at your initial constant speed. The second phase is the mechanical reality. Your foot is firmly on the brake, and the car is experiencing uniform deceleration until its velocity reaches absolute 0.
Let's look at two simple calculation scenarios for practice to figure out exactly how much distance you cover before coming to a complete stop. Scenario 1 is your reaction distance. Because your speed is constant here, the math is incredibly straightforward. Distance equals your initial velocity multiplied by your reaction time. Scenario 2 is the braking distance. Here, we use the velocity-position relation from our kinematic equations. Since your final velocity will be 0, we just rearrange the formula so the braking distance equals your initial velocity squared divided by 2 times your deceleration. Add the results of those two scenarios together, and you've got your total stopping distance.
But I want you to look really closely at that braking equation. The initial velocity is squared. What that means in the real world is incredibly profound. Because of that square, if you just double your driving speed, your braking distance doesn't just double, it literally quadruples. It becomes 4 times as long. This is exactly why speed limits exist. They are directly, physically tied to the unforgiving math of this uniform deceleration.
We've gone from an abstract mathematical dot on a straight line, all the way to understanding the literal life and death mechanics of driving a car. So I'll leave you with this final thought. Knowing that doubling your speed quadruples your braking distance, where else do you think the invisible math of kinematics is secretly dictating the safety limits of the world around you? Keep your eyes open and keep learning.